Okay, my friends, this is exciting. Quantum uncertainty tamed at the University of Arizona. Was it at the heart of this breakthrough is squeezed light, said Mohammed Hassan, the paper's corresponding author and associate professor of physics and optical sciences. Squeezed light is what we were doing using the Venturi, as I will show you. All right, before I get started, I just want you to know they're going to be talking about squeezed light. That is squeezed light. That's light coming forward now, starting to accelerate. As it accelerates, and it has to accelerate because of the Venturi, it squeezes and does what they're talking about in their paper from University of Arizona. So let's get into squeezed light. We've been doing this for a while now. Okay, my friends, this is the University of Arizona. They're talking about quantum uncertainty tamed at the University of Arizona. Now, I want to show you something. This was physics work that I did on light and chemistry and everything. And I did the Heisenberg uncertainty principle, calculated all kinds of things. I found out all of this stuff I was doing was absolute nonsense. Well, not all of it, but a damn lot of it. And I mean, I did a lot. I did everybody. All those Slater's rules and Heisenberg principle and, everything. All the different energies of bonding and everything that they were talking about at this time. And this was like 1970. And all the particle physics and everything. I got a ton of stuff here. So I'm just going to cut right to I moved everything to the front that had anything to do with reality. And here's the only thing that has to do with reality is this right here. Energy, all energy transfers from light, which is atomic vapor. All right? Energy from light to atomic vapor. Light really is atomic vapor. And what that means is it condenses into matter. And the smallest condensed matter that's stable is light, which is a photon. And that's what light is right there, is a photon. This was from the earliest stuff I did with Rod Warren. And this is what the light wave looks like. But the photon's right in there, that little bugger right there. But it's got a big field surrounding it, so that field has to move through. That's why it's a particle-wave duality. But this is totally new, is the dipole electron flood theory. All right, before you can understand the squeezed light, you have to understand dipole electron flood theory. These are the particles, they're the atomic vapor that makes up matter. Protons are made up of equal parts of black and white. This is the difference between the standard model and my model. They had like one big gigantic black particle, which was what they call a positive, and then a few negatives outside, but the negatives were almost no mass whatsoever, and they're little tiny particles, only a few. Well, I have an equal number, and they are very, very energetic. They're not like energetic like they thought. And this is the new model, and there's dipoles, 100% dipoles. Everything is made of dipoles. That's the only two particles that exist. We can separate them. I've shown that. There is no question about it. They can be separated into their electrons and turn into showers. They go into their muons and they stay a mass of dark matter. The neutrinos are the different ones straight up and down and sideways that don't have exactly that shape yet. Gluons are nothing more than heat. They move in and out of things as they become warmer. These are photons, which are two gluons together and bouncing off of something to give you light. There are some differences to a lot of things. The redshift for sure is crazy. Everything's being pulled apart, and they're saying that the reason it's red by the time it hits us is because the galaxy is pulling it away, so it keeps shifting red. No. It's coming at us and getting slower and slower and slower and slower. By the time it hits us, it's red. And if it didn't hit us, at some point it would become just floating around out there doing nothing. They call it the cosmic microwave background. It's just little particles. They're just barely moving. They just keep slowing down. These fields are not some mystery. They're here. There's no question the fields are there. So everything has to plow through them. All right, I said light comes down as atomic vapor. Light is atomic vapor. It's like moisture in a cloud, and it condenses together to make drops of water. Well, this is what every single thing is made of, is the black and the white. This is a subtle change from the standard model. The standard model said you had a huge, gigantic, big black ball in the center and a couple little tiny electrons outside. No, that is not the way it is. They're even numbers. And the black sucks the white particles surrounding it. And depending upon how many they are, is the stability of the atom itself. And that leads to the periodic table, which has only stability at certain quantities. Every one of these is a quantity, but it doesn't have to be exactly that quantity. The way it works is when you have an atom and it has a ton of little particles they call protons and neutrons that make that atom up. You can have a few of them missing, it's still the same atom. It's just an isotope of that atom. You can have more than you're supposed to have, and it's still the same atom, and it's an isotope. I get pretty deep into this, and as you saw, I've been doing this a very long time. This is what happens from the sun. It shoots particles out. Some of them spin very fast. Some of them spin slow, which is the red. The fast is the blue. The sun the moon re-radiates, so it bounces. So you have your very low frequency light, your low intensity light. And I show all of these in our experiments that I did with Rod Warren. This is no guesses here. All right, this is dipole electron flood theory. This was set up for me by a friend, Oscar Rosales, did a fabulous job. This is my interpretation now. There was a secondary interpretation I originally had, which was layered black and white glowy particles. I don't think that's the case. So forget that. And it's 1,839 dipoles, which means one's black and one white together is a dipole. And that makes a proton. All right, neutrons are even numbers, 1840. So that's what makes it up. Not one big black ball and a couple little tiny particles that are electrons. That's not the case. They're even numbers of these, the dark muon and the white electron. And when you put them together, you end up with photons, which are light. This is a gluon, which is the black and the white together. This makes up heat. It's not electricity. Only the white is electricity. The white has no weight whatsoever. Almost no weight. If you take a car and its battery is 1,000 pounds, all right, you with me? 1,000 pounds. If you discharge that battery from being fully charged down to no charge in it whatsoever, it still weighs 1,000 pounds. You fill it back up all the way up full, still weighs 1,000 pounds. The only weight that they can measure, that they have found changes, is approximately 45 thousandths of 1 gram. That's how much energy in that battery pack. You drive 500 miles. If you had to buy gasoline to do that same work in a car, it's at least 60 pounds. We're using less than a couple thousandths of a gram, 45 thousandths of 1 gram to do all that driving back and forth. No combustion, no expansion, no nothing. This is what we need, is that white energy, and I think we can get it. All right, this is fabulous. They use silica to separate the light, and if they change the angle of the silica, adjust the incident angle slightly, one photon arrives later than the other. It's obvious. One will hit here and one will hit down here. All right? Now, that small change is what controls the squeeze. We did it similarly, but we did it with two and created a Venturi. Now he says this is the first ever demonstration of ultra-fast squeezed light. Well, that's not true. We did this long ago. The first real-time measurement and control of quantum uncertainty. Well, that's not true either. We also did that. By combining ultra-fast lasers with quantum optics, we're opening the door to a new field, ultra-fast quantum optics. Yes, well, that field's been open for a while, but nobody's been playing on that field. Now, basically what's going on here is there's a particle inside that wave, and it has a big magnetic field surrounding it. So there's a particle with just nothing but space out to a distance that is a field. I can't really explain it, but these are the particles right here. I hope you can see that, the black and white. That's a photon. That's a photon. They're going this way, and here's what it looks like as they accelerate. They're just starting to accelerate now. And here's what acceleration really looks like as it starts to really take off. Now we're actually seeing the photon itself pulling itself right out of its own magnetic wave. That's extreme acceleration. And it squeezes and crushes here. That's squeezed light. This is light from a pulse red laser, and we do it with green, we do it with blue. It makes no difference. If you do it correctly and you tune the Venturi correctly, you squeeze the light and you end up with muons and electron showers. That's what you're seeing there. And blue is very fast, green is in the middle, and red is the slowest. Now, if you ever know anybody that's a machinist, or you know what a drill is, that is a drill spinning like this. That is the drill bit. It's going through a Venturi. Now, this could be a single, double, triple slit. It doesn't really much matter. And as it hits here, it goes, some go this way, some go that way, but the bulk of them sort of congeal into the center. And as they come through, they push each other apart. They hate each other. That's why you have that interference patterns. You see how perfectly opposed they are to each other? I mean, it's just fabulous. I find it very hard to imagine how precise this is and how these fields push each other apart. Because at this point, coming past this point, it's pretty much only the white particles. Only in the red, they're red. But they are the white particle if you looked at the photons. This is red. All right, this is red. But you see how it's white here? This is just an enormous increase in energy. Luminosity is energy. It went from almost nothing up to enormous amounts of energy and pushed back so hard that right here is where we could see this particle show up right here because it thinks it hit a wall because of the reverse. It's just bam, because this stuff is coming back. Now, I've been doing this a very long time. All right, I found this an interesting statement. One property becomes quieter and more precise while the other grows noisier. Well, let's just look at what this stuff really looks like. This is light. This is light. This is what he's talking about, squeezed light. That's about as squeezed as you're going to get. That is crushed. When it first comes out, it's like this. Light comes out like this. Hold on, let me turn the lights off so you can see better. All right, that's what a light particle is. And these are actual photons. That is an upspin photon. They always have an axis towards the Earth. and this is a downspin. You see how the energetic part is up, the energetic part is down. This is the same photon. It's just it has a spun. You can almost see it spinning here. And it's spun into this one. And then bashed into the backward push to what they call a reverse electromotive force, EMF, reverse EMF. This thing thinks it just hit a wall. That's the only time you see photons, is when they concuss so hard that they're in like a particle crusher, you know, the colliders, the gigantic things at CERN. Then they will split apart, or you can see them. But you can't see that normally. You're never going to see that. It's just, they're all over in here. Every bit of light is the same as that. And it can be green. You see it? Same thing. Now this one's just ready to spin. You see that's a downspin? It's going this way, and it's still oriented straight up and down to the Earth, even though it's going out that direction. That one's overcharged now and going to flip, and that one will go to the front, and it will become an upspin. Green identical to the red, as is the blue. The blue is just too fast. That's through the Venturi, slowing down. And here you can see that it is two whites, but it's just too fast. And they all spin. They spin in a circle. Just like that. This is how light works. The particle is at the tip, and it just goes. It doesn't flap like this. And when they come through the double slit experiments, I'll show you how it works. Okay, I don't know if he could see these things, if they can actually see these, but he's saying that ordinary light is like a round balloon with uncertainty spread evenly between its measurements. I don't really know what that means. But he said squeezed light, also known as quantum light, which is the photons, is stretched into an oval where one property becomes quieter and more precise while the other grows noisier. Well, squeezed light, yes, it's because the fields are crushing each other, and then you start to get, it depends on the speed, it depends on what's it hitting, it depends on the medium that it's going through, it depends on, you know, whether you're starting with the red, the blue, the green, whatever it was. All that stuff plays into account. And then when you force it through a Venturi, all bets are off, it just explodes. Now, I just showed you, these were from the light experiments we did long ago. And we used CMOS. And we could see the same ones Fermilab was seeing. This is 2013. And in 2012, CMOS came out. Well, we used a phone. Rod Warren discovered that he could take pictures of light. And he was just playing around and trying to do a double slit experiment. And what he did was actually picture of light. When I saw it, I contacted Rod. He worked with me for years. And eventually he sort of faded off to, you know, you can only take so much of rejection after, you know, having all the evidence is unbelievable. This was from Fermilab back then. They said the black had a fuzzy thing around it. Yes, it does, because the color is what is being obstructed. That's dark matter. That's not emitting anything. We're not seeing anything there. All we're seeing is that you can't see the glow behind it. The glow behind it is why you can actually see it. So that's his article, Don Lincoln from Fermilab. And these are his particles, and that's the one that has a glow. It has a glowy edge around it. And the only reason it's a glowy edge around it is because it's dark matter, and it doesn't emit, absorb, or reflect. All it can do is obstruct. It's on top of the glow, so you can't see it. We found the exact same thing in our particles. Here's the black one right here, the fuzzy edge around it. These are the glowy ones that are moving forward through the particles in front of them. If you can see those little white dots in the front there, those are the particles that are charging up that part. That's the electron shower part. That would be you have the muon and the electron neutrino. Electron neutrinos can get big or they can get tiny, and that's why they squirt right through the Venturi, as you can see right here. This particle is shooting down here. All right, so this particle is coming down here, but it has a big field around it, and it's pushing everything, so we see the field. The particle's right in the middle, and we're seeing the field. As it comes forward, it's accelerating, and I mean fast, because this is a Venturi. And a rocket ships out of here just exactly like a jet breaking the speed of sound. And you get that ripple effect all the way around it, and a rocket ships right through. Well, this is breaking the speed of light. It's not allowed under the standard model. Everything I'm doing here is not in the standard model. We broke that light apart. We broke the black from the white. That's the strong nuclear force. These are nuclear particles. These aren't big, big, big things. That would be a proton. They're huge. They got 1,839 particles. We're down here. We're down here. And we broke these particles apart. They've seen these at Fermilab. They found them. But they didn't realize, because they just had, when they hit, they get all like that. When we hit, we were using light. So we could see them, and this is actually literally fission. It broke apart. You tell me what fission is. Fission means you break one part away from another part. Fission. Fission. When they come back together, they fuse. What's that mean? Fusion. Fission, fusion. Raw electricity. And this is raw electricity. This is exactly what you need to drive your car. And that's an electron shower. This is from Fermilab too, or from CERN, I can't remember which, but it's high energy particles, muon and electron neutrinos, hitting heavy water. High energy particles. That's the shower. All white, and it fuses all over the place, and the muon just sort of stays black. Precisely what I've been showing here. So I would like to work with these guys if that's their mission here. And I mean, they're teaching, and I think they're supported by the government. I've been seeing a lot of stuff they've been doing out there, University of Arizona, and I got a feeling they're, well, I know I've seen it that was government supported some things. All right, this is the particle accelerating. It's just a particle that's in here, creating a wave in front of it. And then all of a sudden, it's going so fast that the actual little particle is pulling itself out. It's getting glowier and glowier and glowier. And right there, it turns into a white, glowy particle. Bam! It thinks it hit a wall. And that's because of the reverse. And you see how much reverse I'm talking about? You see that over there? That is an incredible amount of reverse EMF. You see how tight those fields are? That is just staggering amount of energy going backwards. And that's why this thing showed up right here. It exploded and showed up as a photon. All these little tiny dots in the air are fields that are in gases, oxygen, nitrogen, hydrogen, whatever it is, water molecules. But this here is just a reverse. This is literally, and I'm not kidding you, this is literally a subatomic nuclear explosion. These are nuclear particles, and they exploded and broke. And they came back to here. That's fission and fusion. Now, I think this should be looked at with a little more, interest. All right, this is what the big guys say. You want to have the muon, the black ball, go on its own, and the white go into an electron shower. The muon neutrino, electron neutrino normally are hooked together. When they hit this heavy water, it's Cherenkov radiation. And that creates electron showers, which supposedly have enormous amounts of energy. Okay, so I showed you that we created electron showers and muons exactly as this shows. Electron showers, now remember this, I'm going to show you something. This is not my work. This, I believe, is from CERN or Fermilab, one or the other. Here's what they show. Remember, we were talking about electrons and muons. This is coming through and creating the Cherenkov radiation, which comes through with just a few particles, and then the cone expands all the way up till you get bazillion particles with energy. The muons back off. They back off. The electrons go up. This is the base tracks of electrons. Bazillions of them. These are low energy. These are high energy. Muons, they bump back out because they can't get through the Venturi. So these are the layers of the showers maximums. Now, what does that do to the energy? Okay, so what does it do to the energy? This is the maximum energy. That little U means energy. It could be potential energy, it could be kinetic energy, but it's energy. All right? This is the number in a shower, max energy. It comes in, it doesn't have hardly any energy at all until it hits the Venturi. And then the energy goes up to 3,000 from basically zero. All right, now, that's thousands of times more energy than you started with. Now, here's the actual electrons, maximum electrons. This is this. Here's the electrons coming in, and they almost back off to nothing. And then when they hit the shower, the Venturi right up here, that's why you have this energy, because you have so many electrons. And what is that? How are they doing this in the particle colliders? How are they hoping to make energy? We did it right through the Venturi. I think we can increase energy very, very quickly and very, very simply. All right, I've shown you, I think, pretty much everything. You've seen the muons and electron showers. You've seen it, well, yeah, I don't know if you saw this. This is the two coming through at the same time through the same Venturi. And the red is so weak, it just gets pushed out of the way as the green goes and makes the red tumble. Remember I said they never spin anything other than like this. I don't care whether they're going this way or that way, they're always straight up and down towards the earth. Except here, because we pushed these away. All right, you see the tumble? You see them how they're round, tumbling like this? That would never, you'd never see that before. Unless you were doing this. And now you see the green concusses back out here. They would normally concuss way out here, but it had to push through the mess that this set up, and it just pushed it out of the way. And you can see, all right, you see that light is made of the black and the white. You see any black over here? You don't see any black. All the black is being pushed to this side, becoming disquiet, while the other side has no black whatsoever. It just has extreme amounts of radiated waves. This side does not have the radiated waves, it has the black particles. It's basically separated the two different distinct properties, which is the wave and the particle. All right, here's what they're saying, is that squeezed light, they can make one side become quieter and more precise, while the other one grows noisier. Well, let me show you what I think they might be talking about. Now, they don't want to do it easy, which we had it easy, electron showers. I showed you the showers. They want to hit proton to protons and make collisions into huge machines. Large numbers of hadrons produced along beam collision axis decay them into hadrons, creating large flux of high-energy neutrinos, which are a lot of damaging stuff because they got big, huge chunks of things. They have created neutrinos and antineutrinos of all flavors. No, not really. This data set, electrons and muons. So they want to get down to the electrons and muons, which is what we started with. The energy of these neutrinos interacting within this big machine they have comes up to 100 billion electron volts to a few trillion electron volts. That's not really that much. It sounds like it's big, but when you're talking electron volts, you're not talking about a whole lot of energy there. You know, this is the beauty of doing this. I didn't even think about this before, was the separation of the actual energy from the particles. But it's exactly what it's doing. I know how this happened, but I just sort of brushed over it. I know that, you know, that's all the dark matter, and there's no dark matter here at all. So it absolutely separated the wave-particle duality, basically. This is incredible as I go back through things. And this one here, I think, this Rod did this one again. I think he used the green laser coming down, hitting a wire, and spraying all this stuff as it hit, causing a lot of energy there. It's getting glowier and glowier and glowier, but it keeps making these spinning discs. I mean, he did some unbelievable, fantastic work. Look at this. These are all Higgs fields. They're coming down this way. This one's getting pinched. So it's changing from the red laser up to blue and then dropping back down as it gets unpinched. And we did this well with the Samsung phone. I did the same things, the Samsung phone with the same laser he had. And it's very simple to do. It's not a big deal. But it takes a lot of time. Look at this. These are all light particles. And the more they gather in one area, the glowier they get. That's why when you force them through the Venturi, they just go crazy. It's all the fields. And then you can tune the Venturi in such a manner as to let enough black through that it pushes a wave of white in front of it. There's a lot that I think I can offer, a lot of understanding. I've been doing this, like I say, a very long time. They know these things exist. They call them Dirac neutrinos. And that's not matter, that's the energy. This is where all the matter is. And it's dark matter, it's muons. The two of them together make a gluon. This is the Majorna neutrino, which is not really a fully fledged black and white yet. And here's what they look like. These are the Majornas. See that one there? Side to side. And these here, straight up and down. They're never going to be anything other than something that goes up and down or side to side to the Earth, just like these do. These are never going to be twisted this way, except for when we hit them with the two through the Venturi at the same time, we made them tumble. Otherwise, you're never going to see that. I know I showed you. Let me just be sure you see it one more time. Where you tumblers go. Here it is right here. That's the tumble. That just doesn't happen. That is a non-occurrence unless you force them to participate in the same space at the same time, one of them being accelerated and the other one not. Normally, if they come through the air, you don't see them. Well, you don't see them in the air. You don't have photons. You don't see photons until they hit something, and then they bounce back at you as light. Photons are a little tricky to explain, but I'm showing them. Of that, there is no doubt. These are coming from a red laser. That's coming from a red pulsed laser. It's a construction laser. Pow! All right, so that's squeezed light, about as squeezed as you can get. You know, the thing about the redshift and the expansion of the galaxies and all that, and how they can tell things are in certain places because of how a light year goes. Well, light goes through different areas here at different speeds. There is no homogeneous thing. All of these things are obstructions to the speed of light. It's not a consistent speed. There's no question whatsoever. It's not consistent. It slows down, it speeds up. And there's fields everywhere. This is just a general shot. I've been working with a guy, he's got a really fancy telescope, and you know, 5-inch Newtonian with all kinds of little gadgets attached to it, and he can see things and do some of this layered. I don't know what he's doing. All I can tell you is the stuff is amazing, and it all shows these dipoles. You glow and less glow. Dipoles everywhere. Look at this. And then Dylan sent me these dipoles. I'm not sure which one this is, but this is one of the planets or something out here. There's our moon, and all of these are dipoles. And all he did was do this with a cell phone. Cell phones use CMOS, and if you do things right, if you know what you're doing, and CERN's using the same thing now. CERN's using the same thing as what we're using from smartphones. You see this? I reported this to CERN and to Fermilab, all of them, back in 2013 or so. And I asked, does CERN use CMOS? Yes, CERN does use CMOS, which is the same as a cell phone. It uses these CMOS metal oxide semiconductor sensors, including modified ones from cell phones. And all the modified means they hardened them so that the big chunks wouldn't hit them so hard. When I went to University of Geneva for particle physics, and I talked to them about using CMOS, and I showed them all my pictures and so forth. At first they said, no, it's impossible. You destroy the CMOS. And I said, no, you guys are using things like that. When you hit your CMOS, you're hitting it with like a Mack truck. We're hitting it with a balloon, a little tiny particle like this. They're meant to work with these. I said, but you can't do it with protons, just smash them with the protons. You know, you're hitting them with a nuclear bomb. What do you expect? The people can't even survive in that. It will kill people. What do they expect from a cell phone? From CMOS? Well, if you hit it with what it's made to design to pick up, which is light particles, then you're okay. And they have modified CERN to use CMOS. Before they weren't using it. They were using charged coupled devices, and it gave you all kinds of problems. But they still want to use these gigantic particles and smash them. For what? I don't know. But when they do, they had to modify cell phones. That's all. They modified them. We didn't have to modify them because we use light.